This slide last time, TCP flow control. Well, actually this is nothing to, we haven't gone to TCP yet. In this chapter we have three parts. First part which doesn't depend upon the transport, and then the other parts which depend upon TCP and UDP. So all this part that we are talking about is general transport so far. So one thing that transport protocols do or may do is flow control, and flow control is simply end-to-end problem. You just want to make sure that the receiver is not over flooded, right? There is a similar problem in the network. Network can be flooded, receiver may not be flooded, but the network can be flooded, and that problem is called what? Not those two people, but somebody else. I really want somebody else to to do here. Anybody else knows what if the network is overloaded? Yeah, congestion. So the idea is, nothing wrong with you guys. You guys are really good, so I appreciate that. But I want to see if anybody else knows it. So the idea is that we are not talking congestion yet. We are just talking about this receiver and the sender. This receiver wants to control how many packets you can send to it. Otherwise, it will be overflooded. It will have to drop it after the packet has reached the receiver. And that is called flow control. So receiver can limit the number of packets. For example, it can say, please send me one packet at a time. So you send a packet, you get the acknowledgement. When you send the second packet, you get the acknowledgement. You send the packet, you get the acknowledgement. This is called stop and wait flow control. Okay. And if L is the distance, L is the length of the packet, L is the length of the packet, R is the rate, it will take L upon R, this much, this width of this thick line, L upon R time to put the packet on the wire, and then it will take one round trip delay before you can put that next packet on the wire. So in this much time, which is RTT, round trip time, plus L upon R, in this much time, only thing you are able to use is L upon R. So the efficiency is, our throughput is L upon R divided by RTT plus L upon R. As an example, suppose you have a 1000-bit packet and you are sending 1000 bits per second. What is L upon R? 1, right. 1 second. So this thick line is 1 second wide. Suppose the round trip delay is 5 seconds. Then your throughput is 1/6. Good. All right. So this is not very good. I mean, you paid for a gigabit, but you are getting only 1/6 of a gigabit, which is not good. So what you do is you say, well, I want to send many packets at a time. So let's say in this case, the receiver allowed you to send 3 packets. So you send first packet and you don't wait for the acknowledgement. You send the second packet, and then you don't wait for the acknowledgement. You send the third packet. Now you have to wait, because the receiver said you cannot send any more than 3 packets. You sent 3 packets, now you're waiting. When the first acknowledgement comes back, you can send one more packet. When the second acknowledgement comes back, you can send one more packet. When the third acknowledgement comes back, you can send one more packet, and so on. Right? In this case, how many packets you have sent in how much time? So let's say in this case, if W is your window, then you have sent W times L upon R. This is the transmission delay. This much time you have used, but total time is 1 round trip plus 1 L upon R. So your throughput is W times bigger. Yeah.
What is W? The number of
W is the window. Yeah, okay. So we call, okay, that's a good question. W is the number of packets that you are allowed, and we call it a window. So in this example, the window is 3.
Is it the max number of packets allowed?
So the receiver says maximum you can send me 3 before you receive the acknowledgement. So I mean you can send 200 packets by this method, but after 3 packets you have to stop until you get the acknowledgement. Once you get the acknowledgement, you can send again. Does that answer your question? So this is the maximum number of what we call outstanding packets. Outstanding means unacknowledged. Yeah.
Why is still RTT plus L?
Yeah. Okay. So let's just see. I'm just remember this point where my laser is. From there all the way to where the beginning of this top edge of this line. That is the time, right? In that time I have sent 3 packets, W packets. So that time is 1 RTT plus 1 transmission. So RTT plus 1 transmission is in the bottom and W times transmission is on the top. Does that? So this is the time used, and this is the actual time busy, and this is the total time pass.
Then it's the time for the act to.
Yeah, see the thing is this whole thing is one round trip. The lower edge of this thick line and then this thin line coming back is one round trip.
Don't you need to wait for the last?
No. So in this round trip you have already sent 3.
Oh, okay. You send another.
And then this thing repeats. Every round trip plus 1 you send 3.
So you don't wait for the entire window to acknowledge.
Or if you can wait, but then the time would be larger, the throughput would be larger. Suppose you wait up to here, right? Then you will have almost like 5 packets sent and and this much time and all that. So it's just this is one complete cycle. All right, so window flow control is good because now depending upon what your window size is, your throughput can go up. Obviously it cannot be more than 100%, but you can use all the way up to 100% depending upon the window, and you can calculate the window from here too as to what the window is required. Yeah.
Throughput should be data per second.
All right, so the question is what is this throughput? This should be bits per second, but this is not bits per second. This is actually percentage. So this one, for example, this comes out 0.5. That doesn't mean 0.5 packets per second. This means 50% of your capacity. So if this link was a gigabit, then 50% of the capacity is 500 megabits per second. So this is actually somewhat, we should call it normalized throughput. This is only between 0 and 1. This cannot be less than 0, it cannot be more than 1. And so this is basically the percentage throughput, or the fractional throughput. Right? It is dimensionless. This is in seconds and this is in seconds. Seconds upon seconds is no dimension. So this is basically normalized throughput. We also call it efficiency. Efficiency is same as this one, which is normalized throughput. So right now it is not bits per second. It is just the efficiency. It tells you 50% efficient or 20% efficient. And this is called a sliding window flow control, because if suppose the window is 5, each packet has a number on it. When you send a packet, you put a number on it, and the numbers could be, for example, 0, 1, 2, 3, 4, 5, 6, 7, and then 0 again, because the numbers have only so many bits. So suppose you reserve 3 bits per number in the packet. So if there are only 3 bits for the number field, then the number would be 0, 1, 2, 3, 4, 5, 6, 7, and then there is no way to express 8. 8 becomes 0. Everybody understand that? With 3 bits, the maximum number could be 7. All right. So the numbers are 0, 1, 2, 3, 7, then 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7. And every time a packet, so basically suppose the receiver wants 5 packets outstanding. It wants to use a window of 5. So as soon as basically, so now let's see what happens. We have sent 7. right? If we send the next packet which is 0, then the window goes down by 1. If the next packet is acknowledged, then this edge goes up. So this edge goes up when the packet is acknowledged. This edge goes up as the packet is sent. And this is the window that can be sent. So the receiver says you can send up to packet number 4, but we have sent only up to 7, so we can send 0, 1, 2, and 3, and 4. So this is the window of the packets that can be transmitted. And this window keeps expanding and contracting depending upon how the receiver allows or how you transmit. And if you keep it in lockstep, this window keeps moving. In the sense that if you just wait for the acknowledgement, as soon as acknowledgement comes back, it send 1, then so this can keep moving. So this is called a sliding window. Sliding window. So here in this example, the window at this point is 3, then it is 2, then it is 1, then it is 0. Then the one acknowledgement comes back. Now the window has moved in terms of the number, sequence number, but the window is right now 0, then it becomes 1, and then 1, 1, 1, and then 0. So this basically remains 1, 0, 1, 0, 1, 0. The window doesn't really ever become more than 1. I mean the leftover thing, right? So anyway, so basically that is how it happens, is that every packet is numbered and there are only few bits allocated for the number, and so the sequence number simply wraps around to 0. And the second concept is that every time the acknowledgement comes back, you are allowed to send one more packet. Every time you send a packet, you are allowed to send one less packet. Yeah.
So if you go back a slide, I had a question about the window. Why would you send 3 acknowledgements instead of just an acknowledgement?
That's an optimization. So the question was, why would you send 3 acknowledgements as shown here? Why can't you just send the last acknowledgement? Well, that is optimization, because if you just send the last acknowledgement, then you won't be able to send these 2 packets early. You will have to wait until the last packet is acknowledged, and then you will send 3 together. That will cause a little bit more burstiness, but it will save some acknowledgement bits. But so the thing is, there is some positive, some negative there. All right. So the first thing was called stop and wait flow control. I gave you the formula before, but here it is again same formula one more time, just in little bit more zoom. So the first bit is transmitted and the last bit is transmitted. This is how long it takes to transmit the packet from 0 to L upon R. Then you have one round trip, assuming that the acknowledgement is very thin, doesn't have too many bits, then you are done. So the total time is RTT plus L upon R. Used time is L upon R, so that is the utilization or efficiency. This is also called T frame, frame time. And this is called prop time. 2 times the prop time plus 2 times plus the T frame time. If you divide both the numerator and denominator by the T frame, this is 1 upon 2 alpha plus 1, where alpha is the ratio of prop to frame time. So U is equal to 1 upon 2 alpha plus 1. This is a very important formula, because alpha, which is the ratio of prop to frame, is very important parameter. And we will be using it quite a bit. And remember, this is always prop to frame. So prop is on the top and the frame is on the bottom. You calculate the ratio, and that alpha value will determine the efficiency of the protocol. And this is actually coming up in a minute again. So basically, right now, you can remember it in one of these many ways. One way is to write like this, another way is to write like this, and third way is to write like that. Okay? All right, all 3 are equal. But remember, alpha is prop to frame. All right, then sliding window. In the sliding window now I have shown the frames back to back. So 3 frames, and then the last edge, bottom edge of the first frame causes an acknowledgement, and therefore the total time is 2 prop plus frame plus W times the frame. So if you were to divide by T frame, you get W upon 2 alpha plus 1. Obviously it cannot be more than 1, so if W is greater than 2 alpha plus 1, all you get is 1. And if you put W equal to 1, then you get the same formula as before, which was 1 upon 2 alpha plus 1. So stop and window is a special case of, stop and wait is a special case of window flow control where window is 1. So you don't have to remember 2 formula, you can just remember 1 formula, and then if you put W equal to 1, you get the previous formula. We can do some examples here just to understand. So let's say we have a satellite link. Everybody knows satellite link. Once the satellite just fell off yesterday or something. Everybody saw the news. All right, satellites are very far away, but they are used for internet and communication. The way it works is that you send the signal to the satellite, and then they send it back to the other part of the world. So if you want to go very far away, or you want to cover the part of the world where there is no other infrastructure, satellite is the best way to get there. So satellite link but takes a long time. So the light itself takes 270 milliseconds for one way, quarter of a second to get to the satellite. So round trip delay is 540 milliseconds. Now if you send a packet which is 500 bytes long, multiply this by 8 to get 4 kilobits. If your data rate is 56 kilobit per second, your frame time is 4 kilobit divided by 56 kilobits per second gives you 4 upon 56 seconds, which in millisecond is 71 millisecond. So everybody can get that 71 millisecond, right? What is the length of the packet divided by what is the rate? So alpha T prop upon T frame is, now this is one way propagation delay. Remember, this is not round trip, so don't get confused here. T prop. One way propagation delay is 270 divided by frame time is 71, so the alpha is 3.8. If alpha is 3.8, 1 minute, I got to fix this. Okay. Alpha is 3.8, then U is 1 upon 2 alpha plus 1 if it is stop and flow, stop and wait, then it is 0.12. U is utilization, efficiency, normalized throughput, whatever you want to call it. The utilization is 12%. 0.12 means 12%. If you paid for 56 kilobit, your throughput would be 56.1 times 0.12. Yeah.
Wouldn't there also be a frame delay on the server whenever it sends the acknowledgement back?
So the acknowledgements are very thin in the sense that acknowledgements might be 8 bits or 10 bits. So that is negligible. We are just neglecting that. All right. Now, so this is a very long link. On the other hand, let's take a short link. A short link, 1 kilometer fiber, will take 5 microseconds for the light to go. And this is something that generally most of us remember, that the light takes 5 microseconds per kilometer, 200 meters per microsecond. Now this is light in the fiber. In the air it takes 300 meters per microsecond, but in the fiber it is only 200 meters per microsecond. So 5 microseconds for 1 kilometer, and the link rate is 10 megabits per second. Suppose you have 500 byte frame, then the T frame is 400 kilobits divided by 10 megabits. So anytime we give you bytes, in the networking world we don't use bytes, we always use bits. All the rates in networking world are in bits. So when we say 56, it is bits. When we say 56 megabits, it is bits. Okay. When you go to the storage world, there they don't specify anything in bits, everything is in bytes. Right? So don't get confused. Get little b and capital B. We use little b and capital B. So bytes is capital B and the bits is little b, if it is only written. Otherwise, if you write the whole word, then it doesn't matter. But if you don't write what is after B, then little is bit and capital is byte. Okay. All right. So back to this. T frame is 400 microseconds. And T prop is only 5 microseconds. So use that formula 1/2 alpha. So alpha is actually 0.012. T prop 1 T frame is 0.012 and utilization is 98%. All right. So now you see you're getting 98% utilization, which is really good. You're not wasting any time, almost. So, how can you increase the efficiency here? Suppose you do have to use satellite link. What can you do to make it better? Can you look at something that you can change? Yeah. No, hold on.
Smaller
Yeah.
packets. You said smaller packets. So
Okay, if you make a smaller packet than T frame, then alpha will become larger and U will become smaller. Anybody else? Let me see. Hold on. Yeah. Yeah. So on the longer links, you need to have bigger frames. That is the same message here. On the longer links, you need to have messages frames bigger, that the alpha is small. Now, another interesting thing is that what about the speed? If this was slow speed, let's say this example, let us take it here. This example was 10 megabits. So that's why it came out to 400 microseconds. But suppose it was 1 kilobit or something like that. Right? If it was 1 kilobit, then this time would be 4 kilobits upon by 1 kilobit would be 4 seconds. And alpha will be 5 microsecond divided by 4 seconds. So 5 upon 5 microsecond divided by 4 seconds. That is a very small number. And U would be, sorry, let me see. If the rate is high, if the rate is low, then T frame is large, and then so that's fine. Okay, so the efficiency is high. I was going to go other way around actually. If the rate is very high, let's say this was not 10 megabits, this was 10 gigabits. If it was 10 gigabit, this number would be a million times smaller. Right? Or maybe 1,000 times. Yeah, 1,000 times smaller. Right? And this number alpha would be 1,000 times bigger, because frame is on the bottom. And this number would be very small. So if you have a long link or you have very high speed link, the efficiency is low. To improve the efficiency on either the long link or on the very high speed link, either case you should use big packets. So either because you are going to satellites or because you are going to very high speed links like 10 gigabit Ethernet, you should use big packets.
So will TCP automatically set packets based off of some parameters for you or something?
No, it doesn't. It doesn't. It just, so the thing is TCP doesn't really know the speed of the link, and then there is not one link, there are many links. These formulas that we are talking about is actually, although they are true for many links, but the calculation that we did here is just for one link. And so when you go, you might go through some low speed, some high speed, some long distance, some short distance. So it's the overall rate that we are talking about here and the overall frame size, but TCP actually doesn't explicitly know this, but you as a user know it. So you can ask TCP to use certain windows, otherwise it will just find it out by experimentation. So here is a graph. Actually, by the way, before I go further, the textbook does not use this kind of formula. The textbook uses RTT in place of T prop and L upon R in place of T frame, and I am going to use it because this is very powerful conclusion which I am going to, and I have want to emphasize that will come back soon later on. So it's very important to understand alpha. The textbook does not use even alpha, but in computer networking, one of the fundamental principles is that the efficiency always goes down for every protocol if alpha goes up. And therefore, you should always try to keep alpha small. Large alpha is bad for every protocol, not just for this window flow control, for error control, for anything we talk about. And that is very powerful thing to know. And therefore, using alpha, using T prop, T frame is better. All right. So, as the alpha goes up, if you plot for various values of alpha, for various values of windows, and here it says N rather than W, because this is not from the book, this is from another book. But basically, the idea is for a given window, 1 means this is stop and wait, 7 means the window of 7, and 127, and so on and so forth. As you increase the window, the total utilization goes up. So, if you had alpha equal to 1, with N equal to 1 you will get this much, but with N equal to 7 you will get that much, and so on and so forth, right? But as alpha goes up, for every protocol, in this case the efficiency goes down. This curve can never go up. So larger window is better. So here think, if you do have large alpha, then you should use as large a window as you can, basically. So if your alpha is 100, you want to use 127 or something. So this is the principle which I have already told you, but this is a general principle and it's not in the book, but it is very powerful, and I want to make sure everybody just memorizes this. For all protocols, and this is where it is, there are no exceptions. For all protocols, the maximum utilization efficiency is a non-increasing function of alpha. So this is also mathematically correct, non-increasing. Non-increasing means the best thing you can do is not increase, remain constant. But this is not possible. All it is possible is mostly it is go down. And different protocols will be compared based upon how fast they go down. Some protocols will go down very fast, some will go down slowly. The best you can do is remain the same. Alright, so the principle is for all protocols the maximum utilization or efficiency is a non-increasing function of alpha, where alpha is T prop upon T frame. T prop is equal to distance divided by the speed of the signal, that is the propagation delay. T frame is the bit transmitted divided by the bit rate, right? And if you bring this up and down, you get distance times bit divided by the bit transmitted times the speed of signal. Alright, now this is important because alpha is this. So large alpha means large what? What can be large? Distance can be large, bit rate can be large. If either of the two cases, if you have a very high speed link or if you have a very long link, alpha can be large. Another reason alpha can be large is if you don't transmit enough bits on that one, if your bit transmitted is small, right? And the speed of the signal is not much you can do about that one. Alright, that is kind of given to you. So we play with these three things so far. I mean, we could play someday with that too, but right now we have three controls. So this is why we call it distance bandwidth product. This is that, distance bandwidth product. Whenever you have a large distance bandwidth product, you have large alpha. It doesn't matter whether the distance is large or the bandwidth is large. It's the product that matters. And whenever the product is large, you have to use large packets. You have to do something about that, because otherwise the efficiency will be very low. All right. So that is not in the book. Please remember that one. I just think that is very important message, and this is the right point to give that message. And basically, it's the alpha that matters. Yeah. Go ahead.
Go back to the slide for a second. So N here is the W.
Yeah, W. Yeah. Yeah. All right. So now we finished the flow control, actually, believe it or not. But basically, we talked about two different methods of flow control. One was called the sliding window, and one was called the stop and wait. And stop and wait actually is simply W equal to 1. So everybody understands the window flow control? Basically, window is the number of packets that can be outstanding without acknowledgement, and the larger window is better for efficiency reasons, and it affects the efficiency. And here is the formula: W upon 2 alpha plus 1. Yeah.
So if larger window is better, when would you ever use stop and when would you ever prefer stop and wait?
Never. So basically, the reason you will use stop and wait is because okay, there are some cases where stop and wait might be okay, and that is because you want to keep life simple. For some reason you don't want to write very complicated protocols or complicated code. That is one thing. Second thing is, if there is a lot of errors, if the error rate is very high, then you don't want to have 2,000 packets outstanding and then you have to retransmit lots of packets again and again. So you just send one, and if it doesn't make it, you send it again, and you send it again, you send it again until it makes it. But most often we just use window, which is more than one. Okay? Any other question? All right. So now we know flow control. Now the next issue is error control. Error control has to do with what do we do if the packet is lost. So here's an example. We send the packet number 1, it is acknowledged. We send the packet number 2, it is not acknowledged. What do we do? Well, we set a timeout, and when the timeout triggers, we send the second copy of packet 2. That is a retransmission. Now it is quite possible that the packet makes it, but the acknowledgement doesn't. Same thing happens. It doesn't matter. So if packet 3 makes it, the acknowledgement for 3 was lost. So then we time out and we send packet number 3 again. Another acknowledgement will be sent, and hopefully that will make it. Yeah.
So is timeout number you choosing randomly, or it's calculated based on the rate of transmission?
Right. So it will be smart enough. The question is, I will repeat your question, is that how do you calculate timeout? It would be smart to calculate the timeout based upon the round trip. Right? So basically, when we get into TCP, every protocol has a different method of timeout. TCP has an algorithm which calculates the round trip, and then there's some safety measure, multiplies it with some number to get a timeout. Does that answer your question? All right, so there are two methods. This is called stop and wait, because you send and you stop and wait, right? Again, another one is something similar to Windows, but in this case we call it ARQ. Another thing is we call it ARQ. ARQ stands for Automatic Repeat Request. Is that you automatically retransmit, right? So go back and ARQ. So the next method is that if you suppose you send 1, you send 0, you send 1, you send 2, when you send 2, the receiver is going to say, sorry, I did not get 1. That is called NAC 1, negative acknowledgement for 1.
Does he always send it right when he gets the next packet?
Huh?
Does he always send the next when he gets
Yeah, when it knows. So the thing is, you know, so okay, hold on. The question is two-part. Question is, do you always send the NAC when you receive the next packet? The answer is, actually, some protocols don't even send NAC. So NAC is just shown in this picture, doesn't mean that we send it at all. So there are some protocols, they may not even send NAC at all. All right? However, in TCP, when we come to TCP, what will happen is if you get 1 and you get a 0 and then you get a 2, you will send a message which says, I got 0. All right? And so if you get twice the same message, suppose when it got a 0, it says, I got 0. And then it got 2, it says, I got 0. That can be interpreted as NAC 1. When you got 2 I got zeros, then you know why you are getting 2 times, because something happened in between. Yeah.
The slide before this, how come the receiver isn't confused when you send packet 3 twice? Like, if it's not sending the acknowledgement back to the sender?
This one you're saying last part?
Yeah. Like, how will the receiver know it's not what they're sending again is in packet 4?
How will the receiver know?
Yeah.
Oh, every packet has a number. So remember sequence number? Every packet has a 3-bit sequence number, so it will say number 3 and then it will say number 3 again.
Oh, okay.
All right, so back to here. So if there is an acknowledgement, either way, either a negative acknowledgement or because there is whatever it is the question is, what do you send at this point? Do you send 1, 2 and 3? You have already sent 2 and 3 and you got the negative acknowledgement for 1. Now you have 2 choices. One choice is you resend everything after 1, including 1. I'm coming to you. Second option is that you just send 1 and then hopefully 2 and 3 will made it and then you will get acknowledgement for 3. Right? If you choose this option where you send everything including 1, that is called go back N. That means I am going to go back the whole thing and I am going to retransmit everything. Even though you just didn't get 1, but I am going to send you 1, 2 and 3. This is called go back N. The other option is coming in the next slide. And the sender has to go back and retransmit all frames. The advantage of this method is that the receiver doesn't store any of the packets which are not in order. So it got 0 which is in order, but 2 is not in order. 2 is out of order. Right? It gets 2, it throws it away, and it sends a NAC 1. It gets 3, it throws it away and sends a NAC 1. All right? And then whenever one of those NACs reaches the sender sends 1, 2, 3, everything. So the receiver is simple. Receiver does not have to cache. We have a question? Yeah.
How come the receiver doesn't acknowledge?
Receiver what?
The receiver doesn't acknowledge.
Oh, no. So the receiver will acknowledge. Here actually I have not shown it, but the receiver would have sent here an acknowledgement for 0.
For 2 and 3 as well.
No, 2 and 3 will not be able to say acknowledge. Here's the thing. Acknowledgement is always cumulative. What that means is if I say I received 2, that means I have received everything up to 2.
Why?
Huh?
Why?
Okay. So the next upgrade is selective acknowledgement, which is little bit more complicated. Then I have to send you a bit map which says, okay, I received 0, I received 2, and I didn't receive 3, and then I received 4, and I didn't receive 5, so you have to send a bit map. That is also next extension. However, that is complicated enough that many people don't implement it. But so if suppose you don't have a normal acknowledgement, means it is cumulative. Yeah.
Did you just say like 4?
Excuse me? Can you just ask him? Can you close your computer, please? And people actually who have the computers, please make sure that you are using computer for something related to the class, otherwise I'll have to shut them all off if I see any activity which doesn't relate to the class. So I had asked about this cumulative acknowledgement. Did you hear any of that? I'm asking you. You just close your computer. But anyway, yeah, go ahead with your question, please. Yeah, what was your question?
I wanted to ask why the sender resends number 3 on. He sends number 3 because he doesn't know that he got the not.
Okay, here at this point, the sender knows that the receiver did not get 1, and therefore 2 and 3 it will not keep, because that is the understanding that the receiver will not cache out of order packets. So it's going to send all of that, and that is go back n. Hold on, right? Does that answer your question? Okay, what was your question?
Wouldn't like an ACK just be like 4 bits though? Like 3 bits with the packet number and then another bit saying you got it or something like that?
No, hold on. So you are going back to selective acknowledgement again. You are saying selective acknowledgement is not that difficult. Is that what you're saying?
Yeah, I mean, why is it so?
Yeah, it's difficult, but that's all. You just take my word for it. In the sense that, here's the thing. Everything is becoming more and more complicated. So in the beginning, when the protocols were for a small speed, for small distances, for small window sizes, there was no need for selective acknowledgement. Today, when we talk about 10 gigabit speeds with windows of 1000, selective acknowledgement is worth it. Right? But for a small number 2 and 3, who cares? We can send 2 more packets, right? So this is for the old days, yeah.
What if the packets get through out of order? They don't take the same path necessarily.
Oh, they just get lost. Out of order means
So
something is missing.
Even
See,
though
think-
they were all transmitted correctly, if they're out of order, then it still goes back and redoes it?
Out of order means, now here, let me see if you understand. 2 is out of order. You know why 2 is out of order?
No, it's not in that example.
Yeah, it is. So anything which is not expected is out of order.
Okay. All right. Then
Anything that is not expected is out of order. So here we were expecting 1 and we are getting 2. So 2 is out of order.
But then if it received 1 immediately after it got 2, it would still say it.
So the 1 is in order, but 2 is out of order.
All right.
Yeah.
That's only why I watch that. If like the network routes it from 2 routers and one packet takes more time than the other, then like 2 arrives before 1. So like 2 is
Yeah,
out.
that's why we don't do path splitting.
Right.
That is why we do not do path splitting.
Another thing?
We don't do parallel paths.
You send 1 and 2 together, right? Like
You just go back to basically 1 will go first and 2 will go on the same path. We cannot
they
send.
go on the same path with the router.
Hmm?
They always go through the same router, the same path.
Well, always is a very strong word. Generally. I mean, it's quite possible that the packet number 1 went there and the link went down. Now there is no way for the packet 2 to go through that path. The packet 2 will go that path. But then the packet 3 will go through that path. Packet 4 will go to that path until some link goes down and then will go. So the thing is, generally the packets follow one path. Is that clear to everybody? What we talked about? Alright, we don't send packet number 1 through this way and the packet number 2 that way and packet number 1 through this way. I mean, again, you can do this. It's not, I mean, it's something long, but then somebody has to keep track of all the things at the end. The receiver has to, keep everything in place for out of order assembly. And the out of order is basically can cause some deadlocks and things like that. So we generally don't do it. Okay. All right. Everybody understand? Go back and ARQ. Right? Everybody understand? Go back and ARQ. Now the next option would be selective repeat. In selective repeat, you just send whatever is not acknowledged and everything should be fine. So basically you got a negative acknowledgement for 1, you send 1, and then when permitted you send 4 and 5, don't worry about 2 and 3. In this case, this works only when the receiver keeps out of order packets. And so you could negotiate when you start the connection, and if depends upon the protocol. If the protocol allows you, then you could negotiate that, okay, I'm going to cache out of order, so you should use selective repeat. Yeah.
So what if we don't care about packet 1 anymore? Do we still have to send it again after the NAC?
Okay, so the thing is, this is error control. Error control means we care for every packet. If you have packets that you don't care for, you don't send through this protocol. Then you send through a protocol which is totally unreliable, has no acknowledgement, you just send it and forget. And there is a protocol like that. Anybody knows that protocol? UDP, right? That doesn't have any of this. But TCP, on the other hand, is a reliable protocol, and therefore every packet is acknowledged, so you care for every packet. Alright, this is also known as selective reject ARQ. So whether it is selective repeat or selective reject, same thing. Alright, now the window size. If your sequence number space is 0 through 7 and you are going to use selective repeat, then your window size cannot be more than 4. Your window size cannot be more than half of the number space. Let's see the example here. So here your number space is 0 through 7, right? You are doing mod 8. And therefore your window size cannot be more than 4 in this example. Reason is, suppose you send 0, 1 through 4, 5, 6, 7 and the acknowledgement for 7 did not make it, right? And then you send 0 because you got the acknowledgement for 6 before. So you are going to send 0. If you send 0, then so what I said was wrong, that you acknowledgement for 6. Suppose you didn't get any acknowledgement and then you happen to have sent 0 because your window was more than 8, then it will be very confusing for the receiver. So obviously your window cannot be more than the sequence number space, but in this example it cannot be more than half the space. So it cannot be more than 4, because if it is 5, then you can get into areas where the numbers are confusing. So where the numbers are confusing, this example doesn't really give that very clearly. So I have to make another example, which I will do next time, not today though. So basically, if you have 3-bit sequence numbers, the maximum window you can have is 2 bits, which is 2 raised to 4, and so on and so forth. That's the result is clear, the example is not clear. Anyway, the summary of this error control and flow control is this. With the stop and wait flow control, the U was 1 upon plus 1 plus 2 alpha. The window flow control, it was W upon 1 plus 2 alpha, 2 alpha plus 1. If you have P as the probability of error or packet error, then the numerator goes down to 1 minus P. So with the stop and wait ARQ, the throughput or efficiency is 1 minus P upon 1 plus 2 alpha. Instead of 1, you have 1 minus P, where P is the probability of loss. For go back N ARQ, here is the formula, which is 1 minus P upon 1 plus 2 alpha P, or W upon this and this, where W is more and this and that, and selective repeat. So these formulas are extensions. We haven't derived them here, but these are extensions of these two formulas that we derived if P is the probability of error. So we have 3 formulas: stop and wait, go back N, and selective repeat. Right? With the stop and wait, the window is 1, so it doesn't really apply. The selective repeat and go back N formula should be exactly the same as stop and wait if W equal to 1. put W equal to 1, these two formulas would be same. And if you put W equal to 1, this and stop and wait would be same. Okay. The main thing is that again similar thing remains like before we saw. I think this is very similar to the previous one, is that as alpha goes up, the efficiency goes down, and here we have drawn these graphs for different values of W and go back n and select to repeat. So now let us see, this is go back n and select to repeat. For n equal to 127, they are very close. For W equal to 7, they are almost overlapping, and for stop and wait, they are identical. That if your W is 1, then go back n is equal to selective repeat, right? That is trivial. If your W is 1, then selective repeat is same as go back n, is same as stop and wait. As the W becomes larger and larger, then the selective repeat helps. So selective repeat doesn't really help if window is small. Now that answers your question as to why we don't do selective repeat, because we were in this range here. Right? Now as the networks are becoming faster and faster, we need bigger and bigger windows, and when we use the windows of 1000, then it does make a difference. Okay? Does everybody understand this conclusion? That the selective repeat was not done before because the windows were not that big. Traditional windows, when I did my PhD thesis, at that time 8 was a large window. Now it is 8000. You know, the largest speed in my days was 1 megabit. Now it is, you already have 10 gigabit. So things have changed. So that finishes the transport layer design issues. The 5 key points of this particular module of chapter 3 is that you can do multiplexing and demultiplexing by a combination of source and destination IP address and port numbers. So you saw as to how the IP addresses and the port numbers are used, both source and destination, so that multiple people can access the same server at the same time and get the correct responses without any confusion. And if you remember, let me ask you this, for some of you on this side of the room. How is the source port number selected? Anybody remembers? No, not you. Somebody on this side, sorry. Nobody remembers? Not you. Anybody remembers on this side? Come on. How is the destination port number selected? Let's say you want to do HTTP. What is the destination port number? 80. What is the source port number? Arbitrary. You could take any number. 3023 is a good number. Alright, so that is important to remember. Port numbers have to be standard for the destination but not standard for the source. Window flow control, then we talked about that today, so you shouldn't have forgotten. Window flow control is better for long distance or high speed networks, which is what we have today. Longer the distance or higher the speed, larger the alpha and larger the window. Okay, now you should just put this in your brain. Basically, we keep this in our brain. In the sense that whenever we see a high speed network, that's what we are working on nowadays. Most of the time is high speed. We want to go from 10 gigabit to 100 gigabit to bigger and bigger, right? We need bigger and bigger windows. Stop and wait flow control is okay for short distance or low alpha. Again, as your alpha goes up, you need windows, and you need selective repeat. Selective repeat is not required if the alpha is small. Right? The window is small. So those are the conclusions. Any questions about any of these conclusions? And I want to particularly you to know about alpha, because I will be asking about that in the exam. It's not in the book, so ask me now. It's a very powerful concept that you just divide what is goes on the top for alpha. Anybody remembers what is the top? Numerator and denominator. Numerator is prop by frame. You should remember that. So as the propagation delay goes up, alpha goes up, things go down, everything else goes down, because basically everything means efficiency goes down. Okay. So the long distance networks are tough to handle and the high speed networks are tough to handle. Alpha, okay? And so that brings us to the end of that. So there is homework 3A. Again, you should do this homework on your own. And when you do it, I can maybe Wednesday, if you have done it by today, so please do it today. Wednesday, you bring your solution. You don't have to submit it. I won't take it. But basically, if you want to check the answer, we can check the answer, just to make sure that you understood correctly. So we are going to move totally from this general discussion to UDP and TCP. Any questions about this? All right, so we'll start with UDP and then move on to everything about TCP. So what is the difference between the two? First of all, TCP provides everything that you will ever need and UDP provides nothing, almost. So this is what we call this is basically unreliable, this is reliable. Because it is reliable, every packet is numbered. Here the packet doesn't have to be numbered, although you could put numbers. Every packet is egged, nothing is egged. Last packet are retransmitted, nothing is retransmitted. Because everything is retransmitted, it may cause a long delay. Here there is no delay, everything just gets there. So if you want to send 1,000 packets, just send 1,000 packets, done. All right, quick and lossy. Correction oriented service. Before you can send the first packet, you have to send a message which is called connection. Please, I want to talk to you. Then you say, yes, okay, I can talk to you, but please send me no more than 3 packets at a time. So all that is negotiated before we can start the first packet. Here there is no connection. You can just send 1,000 packets. Unannounced, connectionless service. Good for reliable and delay insensitive protocol. So this is good when you need the reliability. This is good when you need the delay sensitivity. You want to get things done fast and on time. This is applications like email, HTTP, FTP, remote terminal access. This is applications like telephony, streaming, multimedia. Okay, so what does UDP do? Well, all it does is multiplexing. It does provide multiplexing. I said it doesn't provide anything, but it does provide multiplexing. Multiple people can be talking to a server using UDP. So they have the port numbers. Same port numbers are used for TCP and UDP. So there is source port, destination port. Then the other 2 fields are length and checksum. That's it. There is not, well, and these are the sizes of these fields: 16-bit port number, 16-bit port number, 16-bit length, 16-bit checksum. So it is connectionless. No flow control, no error recovery, no acknowledgement, and provides multiplexing via port numbers. So you could use different ports. Checksum is optional. So this checksum is optional and it applies to pseudo header, same as TCP and UDP segment. If not used, it is set to 0. If the checksum is 0, means it is not being used. And this protocol, UDP, is used by network management, DNS, multimedia, that are last order and delay sensitive. So we already talked about multimedia, but why for DNS and why for network management? Well, let's say you want to make a query to DNS and ask what is the IP address for www.google.com. Now you could set up a TCP connection. Then you could say, well, okay, can I talk and this and that, and then you say, well, I have only one simple question: what is the address for www.google.com? And it could send you the answer and then say, okay, now close the connection. So when you have just query response, only one query, one response, then we prefer not to do the connection. All right? We just send a packet request, the response comes back. If the response times out, we send another request. Same thing for management. Management command is like to the router, how many packets have you dropped, or how many packets have you forwarded? That request can be sent to the router, and the router can respond to that request. And if it doesn't make it, you send it again. All right? So rather than have the transport provide the reliability, you just provide it in the application if you need it. Many applications don't need it. For example, multimedia doesn't need it. Multimedia, if you send some voice, if it didn't make it, blip. You just play a blip and move on. Actually, they don't play a blip. When we come to multimedia, what they do is they replay the previous sound. So when sometimes you listen to my lectures online, everything is recorded, right? Listen to lecture online, and if a packet is lost, you will hear the same thing again and again. Like it might say 2, because the packet 2 was the last one that made it, and then 2 or 3 packets didn't make it. So it just plays the same sound again. All right, so this is TCP. I think we have 8 minutes more. Okay. So any question about TCP? Sorry. Yeah, UDP. Yeah.
I have a question about like streams multimedia.
Yeah.
If the packets get dropped, why does it sometimes restream and sometimes, like if you're watching a movie on Netflix, sometimes it'll just stop and sometimes
Right.
reconnect and sometimes it'll just pause for a bit.
Right. So I think, this is because I haven't verified this, but there are 2 connections there. One is a control connection and one is a data connection, just like FTP. The control connection, uncontrolled connection, you send a command like restart, go back, cancel, rewind. Those commands go on the control connection. Those are very reliable. Those have to be sent reliable. So if you want to rewind, you just send a rewind command, and that goes with TCP connection. All right. In parallel, the data is coming on the UDP connection. Actually, it's not a connection, but if you want to call it a connection, so it comes on a data path. All right. So when your command gets lost, then it doesn't have any choice but to wait. Yeah. Was there a question here? Sorry, I stopped.
You just said,
Yeah.
well, if you stream on like YouTube, it still uses TCP to download all the data reliably. Just like buffers, and then you view it. So it's not real time. It's not like live stream where you have UDP.
Now, here's the thing though. So that's why I said I think. Now the thing is, the data packets, now UDP, every streaming application will do buffering. Every streaming application does buffering. Now, if UDP uses TCP for data connection, that is their decision. And so, that way they don't want to miss anything. But it would be many applications. I could think of another application where I would use UDP for data. Yeah.
Are there times where it's worth it for, if you don't want all the setup of the TCP socket, but you still want maybe some reliability, so you try to would you ever want to emulate some parts of TCP on UDP?
Yeah. So the question is, would you ever want to emulate some part of TCP and UDP? The answer is that's what exactly is done. So if you want any reliability, some applications want some limited reliability, in which case maybe they want to just retransmit once, and if it doesn't succeed, done. I don't want to do second retransmit. Suppose you have an application where you want to retry at least once, but not more than one. TCP will keep retrying until that is done, right? So they will do it in the application layer. you can do all of this, what we talked about in the transport layer could be done in the application. The application could do the sequence numbers, it could put the retransmission, it could have a timeout, everything. Except that since so many applications needed all this stuff, they said let's just do it in one layer called TCP. So yes, you can do, whenever the UDP is used, a lot of things do go into the application. Does that answer your question? Okay. Any other question?